Okay, perfect. Okay, so my idea is to share just a quick presentation with all of you of the technical implementation of the vector data type and how we solved some of the challenges that we encountered. But most interesting for me is to show real examples. So I'm gonna go through the implementation details, but again, if someone wants to see the complete implementation or have any doubts, you can contact directly to me, and we can have a session with the complete team. Okay. So let me know if you see the presentation. I hope you see it.
Yep, looks good.
Yeah, maybe it's a little bit too small, so I'm gonna zoom in a little bit. Okay. So basically, as I was mentioning, no, we implemented vector data type, no, that will extend IBM Informix natively to do vector search, and of course, in today's world, no, we will be able to perform RAG. Okay. So the first thing that we need to understand is that more and more apps need to search by meaning and not just by keyword. Okay, and this kind of data needs to live close to the rest of your information and respect the same access rules, etc. Right? So the usual approach that that people are using, no, to solve this today is to add a secondary database, no, just for this kind of search, and that works. But then you need to have two systems, no, that you need to keep in sync. You need to manage two backups. You need two teams on the call, etc. No? But the real danger is also that if something gets deleted in the transactional database, you know, where your data lives, you need to make sure that you also delete it from the vector database, right? And this can cause mistakes, no? And this information may show up in search by mistake. So our approach is to implement this vector search in the engine, okay? And what we did is, we use the DataBlade extensibility model that Informix has, no? And basically, we have two components, okay? The first one is the actual vector data type, okay? So this data type has variable length, no, stored in line in the row, no. It implements, of course, the input, the output, the send, the receive, and of course some operations, no, like cosine similarity, L2, L1, plus other arithmetic operators. And then what we did is that we binded, no, operators like plus, minus, dot, equal, no, to make them work natively. Okay, that's the first element that we implemented, no. And the second one, which is actually the most, I would say, sophisticated one and the important one, is the HN SW index. Okay. What we did is we implemented the virtual index interface in order to be able to search in a fast way. Okay, without this index, this implementation would be very slow. Okay, so here we have the extensibility, no, the DataBlade extensibility. We have, of course, the SQL engine, and then we have these two elements that I was explaining, no, the vector data type and the virtual index interface, which implements the HNSW algorithm. Okay. How we store the vector? Well, we store it in an Informix row, no? And what we did is that we needed to support the dimensions that model providers, no, like OpenAI or Google, no, or Cohere provide. So we know there's a limit, but we can store up to 8,000 numbers per list, which is more than enough, no, to cover today's model embedding dimensions. Okay. Well, then you can see here, no, a little bit what I was mentioning before, the C functions, no, and the actual math definition, no, and the comparison with we compared with PG vector operator, no? And we have identical operations already implemented in the system. Okay. Now, this is also important, no? Why we did some trick, no, to make it faster, no, even faster, apart from what I'm going to show you now in a bit. But basically, we did a trick in the code that comparing two lists, no, takes a lot of small math steps, no, and modern computer chips, no, can do several of these small steps at the same time. No? And what we did is basically this, no, we can detect the type of machine, no, and based on what it supports, the implementation goes through one direction or the other, no? Which helps in the performance. Okay. This is the second component, no? The hierarchical navigable small word graph, no? You have to imagine this as a map with highways, no, basically, and small local roads, no. So the first lane is like a highway, no. It lets you travel quick from one point to another, but then you can move to the second lane, which then can be used to jump to the level 0, no, where you have more dense nodes, no, and implementing this, no, this index helped extremely, no, in terms of performance. Okay, so well, just for you to see, no, a little bit the implementation, no. Here, as you can see, no, as I was mentioning, we have the vector data type. Okay, so really quick, but you will see, no, that as we were seeing on the keynote, no, we have the vector input that is capable of receiving the vector, no, and understanding it. We have the vector output, the send, receive, and all the utility functions, no, to work with this vector data type. Okay, and then we have the index, no, that implements the hierarchical navigable small word, no, and yeah, this is the implementation of the index, and then we have, of course, the install, uninstall of the index, and install and uninstall of the vector. Okay, so what I can show you now is we have some demo corpus that we have processed, no, and generated the chunks, no, the text chunks. We have used OpenAI text embedding model, and basically this is the load, no, just as a demo purpose, no, of these embeddings, no, of these vectors. Okay. So I can go, for example, to DB access, no, and sorry, I can open up the editor, and here I have just some sample queries, no, that will be able to search, no, in this database, no. So if I run, sorry, let me do it. What's wrong here? Use editor, check. Let's see. Yeah. So here you can see that the select, no, search, no, across this corpus, and it returned the ID, the file name of the document, no, and the distance of these vectors. Okay. Of course.
Sorry to interrupt. Are you sharing something right now? We're just seeing the
Sorry.
document.
Oh, sorry. Okay, I shared only the one screen. Huh. One sec.
Yep.
Sorry, because then you did not see.
All right,
this.
that looks way better.
Okay, you did not see this part. My fault. Sorry for that. I was showing the. You see now the screen?
Yeah, we see the vector project.
Okay, so yeah, I was showing the vector data type implementation, the index implementation, and the install, no, of both the index and the vector, no. And then what I was showing is we have some demo data, no, that what we did is we previously generated embeddings for this corpus, this sample corpus, and inserted this data into the database, no, and then we have some sample queries, no, that we can run. Okay, we can run against this Informix database, no, and returns the records that match this query, no, and as you can see, we have, of course, the distance, no, of the vectors. Okay, as I was mentioning, of course, you need to generate the embedding, no, for the user query, no, and then use the Informix select, no, to search for similar vectors, right? So this is just an example. Now let me share entire screen. I will share my entire screen now. Okay, I hope you see the screen, the whole
Yep,
screen
we
now.
do.
Okay, so more examples, no? Here we have Scientific American from what, a lot of years, as you can see here. We can open up the document, no? Where we can see the actual document, no? And what we can do is we can use the Informix vector data type, no? To query against all these documents that are stored in a physical database table. Okay, so I have some sample queries here that we can use. For example, let's try this one. Okay, so now you will see that under the hood, what this rack agent is doing is basically, well, it has generated an embedding for the user query, which, one second, I will show you. Come on. Sorry for that. One second. Well, I will try to show you the afterwards. But basically, what we did, no, is we generated an embedding for the user query, no, and under the hood, no, what we did is we performed a SQL query against this Scientific American database, no, and it returned several documents that are then passed. We can then obtain from the document ID, no, we can obtain the associated text chunk, and then we can pass the relevant text chunks to the LLM and say, okay, based on the user query, reply to the user in a concise manner or whatever you may want. So we're able to do this kind of typical workflow, no, to search across, in this case, a lot, no, of PDF documents, large PDF documents. No? Another use case that I can show you is internal documentation. Okay, our system has has a lot of internal documentation. No? We have a server-side library with a lot of packages, which of course are only known by the framework. Okay, so what we can do is we can create a new chat here and say, how does the ax.db package work? Okay, AX is an internal package from the framework that, of course, does not exist on internet. It's internal documentation, no? All these documents, for example, if we open up one of these, are stored in an Informix database. And again, what we're doing now is we're doing an embedding for the user query, no? And this agent is now using, no, the Informix database to perform search queries against the whole system. No? So hopefully now we will be able to see, no, the same kind of response, no, of how in this case how this package works in the system. Okay, we can apply this to any use case. I wanted to show you the popular ones, no, which are of course searching about internal documentation that is not available in the public surface, no, but apply it to anything that you want, and works natively, no synchronization between another vector database, and the benchmarks are quite good. We compare to other frameworks, you know, like PG Vector, and it's quite good. In fact, the vector dimensions, if I'm not wrong, are higher. No, we support higher dimensions than PG vector, I think. I don't know if you have any questions or if you wanna ask me something about any specific area. But again, if you want to get more in detail about the actual implementation, we can share the code, no? And you can install it, test it, and make it yours. Okay, that's the idea. Tom, how you see it?
I think Tom was dropping off for another meeting that he had to go to.
Yeah,
Thank you,
we're-
Javi. There he is.
Yeah.
Thank you. I don't know where the chat is. We have here the chat. What's the minimum version that is supported? Minimum version, I think, if I'm not wrong, but again, we need to. I will need to check this with the team, with the implementation team. But I think it's 14 dot something. But let me double check it, and I can send you the PDF document with the complete implementation detail and minimum requirements.
I don't see other questions, Javi. Thank you for your time.
No problem. Okay, can you share the documentation for this? Yeah, sure. I will share it if you think that is fine. I will share it with the IIUG team, and they can broadcast it to all the people that have joined. Okay.
And we will post the recording here in a couple days.
Perfect. I will send you the documentation, and then you can broadcast it to everyone. Okay.
Okay. And we've got a next July. We're going to have a session by Tom Beebe coming up.
Great.
It should be posted in the next couple of days to register for that one.
Excellent. Okay, so thanks everyone for joining. Really appreciate it. And again, I will share the documentation. If you have any doubt, you wanna see anything else more in detail, please feel free to contact us. Okay. Okay.
Have a good day, everybody.
Good day. Thanks everyone. Bye bye.